Okay, picking up with benzylic bromination, again, we need a benzylic position. I'm only illustrating one here because we have to have at least one hydrogen. If we react this with NBS, now NBS, we can use abbreviations in organic chemistry, but it has to mean something to us. NBS stands for N-bromosuccinimide. So this part is derived from succinic acid. It's a cyclic amide here, so that makes it an imide. And then the bromine is on the nitrogen, so N-bromosuccinimide. And what this does is it provides a low concentration of Br2 for the reaction. We also need a radical initiator, benzoyl peroxide, which maybe you've heard of before. Benzoyl peroxide is a key ingredient in many acne treatments. So this creates oxygen radicals. There is an oxygen-oxygen bond there, which is readily cleaved by the heat from your skin or from light, and produces an oxygen radical. And maybe you've heard about oxygen radicals. We take vitamins with radical scavengers in them. That's a great marketing strategy out there today, because those oxygen radicals cause aging in the body. And so in the case on our skin, it kills the bacteria that can contribute to acne. So under these conditions, we get a single bromine at that benzylic position. Of course, once we've added the bromine, the reactivity goes down, and that contributes to the selectivity also. So now, how does this reaction occur? What's the mechanism? All right, so in this reaction, we're going to generate a hydroxyl radical, or sorry, an oxygen radical, which I'm just going to illustrate as OR. It then abstracts that benzylic hydrogen. Remember to push the arrows for radical reactions. I'm using the fishhook arrow or the single-headed arrow, which pushes one electron at a time. I have now made that bond. Of course, that's a benzoic acid, just showing it this way for simplicity. And we have made a radical at the benzylic position. And of course, that radical is stabilized like all other anions or cations at the benzylic position. It is delocalized. And I'm going to draw a resonance form over here for you. Remember, that squiggly line there means that the geometry is undefined. I don't want you to think I'm trying to define a geometry. Of course, in benzene, it doesn't matter, but we might get to substituted benzenes where there could be issues there. I don't want you to be confused. We make this radical resonance form. That's just a resonance form. Okay? Of course, we would say this resonance form has lost significant portion of its aromaticity. So this is not the most important excuse me, resonance form for this intermediate. Then this intermediate, and I'm going to push the arrows a slightly different way now, can react with the Br. Okay? can provide the product, and it provides a bromine radical. Of course, there are 3 lone pairs around there I'm leaving out for simplicity. This can then react with another starting material, and that's the chain propagation. Remember, radical mechanisms have initiation steps, they have propagation steps, and then they have termination steps. And for a good synthetic reaction, we need about 10,000 cycles through the propagation step to get a good yield of our desired synthetic product. And then, of course, termination. If you recall, termination is when we have 2 radical species, say 2 benzylic radicals that I'm going to just illustrate R and R here as a reminder for you. When those 2 come together, they form a bond and there's no radical left to carry on the chain. This is termination. Okay, so we need propagation, termination, and of course this is initiation. All right, side chain reactions.